In this video, we're going to take a look at how to solve an equation that has trig expressions in it. So your first step is usually to add or subtract terms to get everything on the same side of the equation. Most of the time, 99% of the time, you want to have all of your expressions set equal to 0. Now, a comment I do want to make about this to emphasize it is you should not be multiplying or dividing both sides of the equation by any trig expressions. If you do something like divide everything by sine of x, you might lose some of your answers, and you don't want that to happen. Step 2, usually you can just go straight into factoring the expression. It may be a GCF or a difference of squares, whatever the case may be. But sometimes you may also have to use a trig identity, especially if you're doing like the trinomial factoring where you break it into two binomials. You might need to use one of those Pythagorean identities to make sure everything shows the same trig expression throughout. You can't have some sines and some cosines if you're doing the trinomial factoring. Once you've done that, as long as you have your factors being multiplied together set equal to 0, then you can actually do each factor separately set equal to 0 and solve those equations independently. And then you're going to use your unit circle to evaluate those simplified expressions you get. So if you get an equation that says something like sine of x equals 1/2, this means look at your unit circle, find where the y coordinates are 1/2, and then state the angles that answer that. In this case, the solutions would be your pi over 6 and your 5 pi over 6 values, because that's on the unit circle where you should see a y coordinate of 1/2. So here's our first example. And again, please do not divide both sides of the equation by sine of x. Yes, that would make things look a lot simpler and easier, but we would actually be losing a lot of answers if we did that. So we cannot take that step. Instead, I'm going to subtract 2 sine of x from both sides of the equation. So now I'm going to have sine of x times cosine of x minus 2 sine of x is equal to 0. So that's our step 1 I was describing. Move everything to one side of the equation, but don't do it by multiplying or dividing. Do it by adding and subtracting instead. Next, I have 2 terms here, and both terms have a sine of x in them. So I'm going to take the GCF out of sine of x. When you take out the GCF, you're essentially dividing each term by that GCF. So if I have sine of x times cosine of x, and I divide that by sine of x, the signs cancel, and I'm left with cosine of x. If I have negative 2 times sine of x, and I divide by sine of x, the signs cancel, so I'm left with minus 2. You can always check your answer from your factoring by redistributing. So if I did sine times cosine and sine times negative 2, that would bring me back to sine times cosine minus 2 times sine of x. So now that I've done the factoring, I have sine of x times cosine of x minus 2 equals 0. So these two factors, I can actually split them up into 2 different solutions at this point. This only works when your equation is set equal to 0. It's called the zero product property, because the only way for 2 numbers being multiplied together to equal 0 is if one of the numbers equals 0, one or both of the numbers. So if you have an equation set equal to 0, whenever you have things being multiplied, you can set each of them separately to 0 like this. That way I have smaller, easier equations to solve with. Sine of x equals 0, that one's done. There's nothing else to move away from the sine of x. It's already by itself on one side of the equation. But for this second equation, I could add 2 to both sides, which would give me cosine of x equals 2. Next, you would be looking at your unit circle, and I'll show you where to find these solutions on there. So for the first part of our solution, we said when is sine of x equal to 0, which means you need to look at your y coordinates and find whenever that equals 0, and then your answer is the angle measurement. Now I'll show you back on the previous slide, but I said your answer needs to be between 0 and 2 pi. It has a bracket on the 0, but it has parentheses on the 2 pi. So even though both of these represent a y coordinate of 0, I would be excluding the 2 pi answer and writing 0 as one of my answers. The other place that I see a y coordinate of 0 happens over here. And the angle for this one is pi, and that is between my 0 and 2 pi range. So my answers for when does sine of x equal 0, those are going to be 0 and pi. Now the second factor we found was when is cosine of x equal to 2. So if you're looking at your x coordinates, you'll notice that the x coordinates never go bigger than 1 or smaller than negative 1. So that second factor we found, when is the x coordinate equal to 2, it never happens. So there actually aren't any solutions that come from that part of our equation. So the answer to sine of x equals 0, we found that was 0 and pi. Remember, this is why I'm not including 2 pi. It says do not include 2 pi as an answer, but do include 0, since those two are the same thing. And for cosine of x equal to 2, there are no solutions to this. This does not happen on the unit circle. It can't happen. So when I'm writing down my final answers for the problem, I would only include the 0 and pi. Conceptually, what we've just done is we found the 2 radian angle measurements that you could plug into the original equation that would give us a true statement. So these 2 sides of the equation will not be true unless you're using the angles of 0 and pi, because sine of 0 times cosine of 0 will equal 2 times sine of 0, or sine of pi times cosine of pi will equal 2 times sine of pi. That's what we found. Sometimes there's a problem with the answers you get in that final step. Like you might find 0 and pi over 2 and pi are answers. However, when you try to plug them back into the original equation, they may not actually give you a true statement. The situations where this happens, it's because the angles you're plugging in, they might be undefined for some of your trig functions. So the best thing to learn here is that if you're looking at the unit circle, we know that tangent is undefined for pi over 2 and 3 pi over 2. So basically what happens is if you have a tangent of x anywhere in the original equation, if you got an answer of pi over 2 or 3 pi over 2, then you have to cross it out. You can't include it as a final answer. It's what we call an extraneous solution. It's like a fake answer that we got it from going through the solving process correctly, but if you actually try to plug it into the original equation, it does not work because it gives us an undefined value instead of a true statement. So the values to look for are pi over 2 and 3 pi over 2. You need to cross those out whenever you have tangent of x or secant of x, because both of these functions are undefined for those angles. If you have cotangent or cosecant anywhere in the original equation, then you need to eliminate answers of 0 and pi, because these functions are undefined at these two angle measurements. So the idea is just once you get all the way through, make sure that you don't have any of those potential fake answers, but they only occur if you have those specified trig functions in the original problem. Pi over 2 and 3 pi over 2 are perfectly fine answers to use as long as you don't have tangent or secant in the problem. So let's look at an example with an extraneous solution on it. Again, do not divide both sides by cosine of x. You would lose answers if you did that. So instead, I'm going to take the cosine of x times tangent of x, and I'm subtracting cosine of x from both sides of the equation. So now I have everything set equal to 0. Again, I'm going to factor this. The factoring here will be another GCF step. So I'm going to take cosine of x out of both terms. And if you divide the first term by cosine of x, the cosines cancel. You're left with just tangent. And then negative cosine of x divided by cosine of x is -1. A lot of students accidentally write 0 there, but you're dividing cosine by cosine, which is 1, not 0. So now I have my 2 factors set equal to 0, which means I can set each of the factors equal to 0 separately, which makes the solving process a lot easier, because now I have smaller equations to work with. The equation on the left is done. There's nothing else to move over. But for this equation on the right, I could add 1 to both sides of the equation. So instead, I'm going to be looking for when does tangent of x equal 1? And at this point, we're going to look back at our unit circle. So for the first part of our solution, we have cosine of x equals 0. That means find the x coordinates that equal 0. Here's one of them. So my answer for this part is going to be pi over 2. And then if I keep going around all the x coordinates, there's another one that equals 0 down here at 3 pi over 2. So those are 2 of my answers for now. And then the second part of our equation came from when does tangent of x equal to 1? Well, I wrote the tangent values around the outside of the unit circle, so you can see that here's a tangent value of 1. So that answer would be pi over 4. And then if I keep going around, there's another positive 1 down here. So my other answer would be 5 pi over 4. So here I've written in the answers we got for when the x-coordinate equals 0 and for when our tangent values are equal to 1. But since I have a tangent in the original equation up here, I have to eliminate my answers of pi over 2 and 3 pi over 2. Those are extraneous, so I do not include them as part of my final answer. So the answers I would be circling in this problem are just the pi over 4 and 5 pi over 4. And again, that's because what happens is if I try to plug pi over 2 into the original equation, well, cosine of pi over 2 is equal to 0, that's fine, but then tangent of pi over 2 is undefined. So you can't do a 0 times pi over 2 value. So when you try to plug it into your equation, you end up with some undefined values, so you end up with a false statement. So that's it for the notes. Thank you, guys.